Greetings everyone, my name is Mingazzi Lorenzo. I'm a PhD student from the University of Parma, and together with Professor Francesco Freddi, we performed phasefield simulations of cover cracking in corroded reinforced concrete beams. The presentation is structured as follows. First, the motivation and the objectives of our research. Second, an overview of the physical problem is given, as well as the details about the model used to describe it. Eventually, the numerical results are presented, starting from the validation of our model and followed by the two numerical tests we performed, and lastly, some concluding remarks about our research. We decided to focus on this topic because the corrosion of reinforcement bar is one, if not the most common degradation phenomenon for reinforced concrete structures. And due to the corrosion process, the cross-section area of the rebar suffers a reduction, which translates into several safety issues that might rise into the structure, such as a reduction of the bearing capacity, a reduction of the ductility, and a reduction and or a complete loss of the bond between the concrete and the steel rebar. And moreover, due to the formation of rust deposits around the reinforcement bars, a swelling phenomenon might happen, leading to cracking and spalling of the concrete cover. We decided to focus particularly on this last aspect, and we aim to develop a predictive model which is capable to provide accurate estimates of the carbonation-induced corrosion cover cracking problem for reinforced concrete structures. The full phenomenon could be subdivided into three different phases. The first one consists into the carbonation of the concrete, which happens due to the diffusion of pollutants present in the air into the concrete pores, which lead to reduction of the value of the pH of the concrete, especially around the rebar. This is a critical aspect, since the reduction of the pH leads to a depassivation of the steel rebars, and the corrosion process can be started from the oxygen and the water in the proximity of the reinforcement bars. And due to the corrosion process, a rust deposits might form adjacent to the rebar and creates a swelling phenomenon, which lead to overpressures in the surrounding concrete, which might suffer from cracking and spalling phenomenon. The carbonation process takes place and starts with the carbon dioxide diffusion within the concrete pores in gaseous form, and eventually it dissolves into the pore water as well as the calcium hydroxide, which is present in the cement paste, and react together to form calcium carbonate, according to the neutralization reaction reported in the presentation. The calcium carbonate is, however, less soluble and occupies a larger volume compared to the calcium hydroxide, which lead to the phenomenon of the pore clogging. Therefore, this translates into a lower porosity of the cement, of the concrete, and a change in the mechanical properties of the concrete as well. Moreover, the value of the pH is lowered, and once the carbonation front reaches the steel rebars, the depassivation of the steel rebars takes place as well. In order to account for the changes in the material properties, we introduce the material modulation function, which are function of the ratio between the current concentration of calcium hydroxide compared to the initial concentration. The model for the carbonation process is based on the standard diffusion reaction equation system. In particular, for the carbon dioxide, the diffusion part is governed by the Fick law, with a diffusion coefficient which depends on the carbonation and the damage state of the material. The first one to account for the change in porosity, and the second one to account for the fact that CO2 can freely move through the cracks in the materials. For the reaction part, we have that the reaction rate is multiplied by the porosity and the volume fraction of the pores partially occupied by water, because it represents the actual condition in which the neutralization reaction takes place. For the calcium carbonate and for the calcium hydroxide, we have only the reaction term. For the calcium carbonate, it accounts for the formation of the new material, while for the calcium hydroxide, accounts for its consumption during the reaction. Once the carbonation front reaches the reinforcement bars, the passive layer protecting the rebar from the corrosion is lost, and therefore the corrosion process can start due to the presence in the adjacent areas of oxygen and water. The carbonation process lead to a generalized depassivation of the reinforcement bars, which translates into a generalized corrosion process. The corrosion process is characterized by two semi-reactions, one for the steel anode oxidation and the other one for the oxygen cathode reduction, which when summed together, they provide the complete corrosion reaction. In order to model the corrosion process, we adopted an electrochemical modeling approach. The electrochemical modeling for the corrosion process is structured as follows. So first, we calculate the electrical potential for each of the two semi-reactions via the Nernst equation. Once we have the two potential, we can obtain the value of the corrosion current density using the Butler-Volmer equation. And once the corrosion current density is known, it is possible to evaluate the change in radius due to the formation of the rust layer using the Faraday law. From the change in radius, then we can obtain the swelling associated with the deposits of rust by dividing the change in radius by the value of the initial radius of the rebar. Once the value of the swelling associated with the formation of rust deposits is known, we can proceed to describe and model the cracking or spalling phenomenon of the concrete cover, and we choose to approach this problem via the phasefield approach for brittle fracture. In particular, this is a variational approach based on the Griffith theory of fracture for brittle material, where damage represents a transition between the broken and unbroken areas of material and is represented using a scalar smooth field. In particular, crack nucleation, formation, and evolution is described via the minimization of a two-field energy functional, which depends on the displacement field and on the damage field. In the phase field model we use to describe the formation of cracks within the concrete cover, we considered a traction compression energy split for the concrete strain energy, allowing to apply the damage field and the evolution of damage only into the areas under traction condition. For the steel, for the rebar strain energy, we consider only the elastic part of the strain tensor. This permits to introduce the swelling obtained from the corrosion process as a loading parameter. And should be noted that for both the strain energies as well as for the fracture energy, the material modulation function are included in order to account for the changes in the material properties due to the advance of the carbonation front. Lastly, the total energy functional is obtained as the sum of the different energy terms integrated over their respective domains. The complete numerical model is therefore structured as follows. So for every time increment, we solve first the carbonation problem, obtaining the carbonation profile and the value of the pH inside the concrete. If at any point around the rebar the pH is lower than 9, then we can solve for the corrosion process, obtaining the swelling associated with the rust formation around the rebar. And from the value of the swelling, we can move into the damage problem, obtaining the updated displacement and damage field associated with that swelling value. For now into the numerical test, and we first proceeded with the model validation for both the carbonation and the corrosion process. And as can be seen from the presentation, The numerical results we obtained are very close to the numerical results present in the literature, which are a good approximation of the experimental results. For the corrosion, we also found that the values of the corrosion current densities for both the case of the passive and depassivated steel rebars are in good agreement with the average values present in the literature. The first numerical test we present is the double-side diffusion, in which we considered a squared specimen with a 16 millimeters diameter bar placed in the center, with a flux of carbon dioxide coming from the left and bottom side at a natural concentration, and the vertical displacement are blocked on the top side of the specimen, while the horizontal displacement are blocked on the right side of the specimen. The simulated time of this test is 20 years. The video reports the results for the double-side diffusion test we performed, and in particular we have on the left side the evolution of the concentration of the carbon dioxide. On the central panel we have the carbonation profile, while on the right panel we have the damage field evolution. And it can be seen how the carbonation profiles actively affect the crack pattern, and especially now when the carbonation profile reaches the steel rebar, damage nucleates and evolves toward the side from which the carbonation profile reaches the steel rebar, as these are the areas where the swelling of the rebar starts earlier. For the second test, we considered the same geometry and initial conditions as well as boundary condition of the previous experiment. However, we introduced a notch on the bottom side to evaluate the changes in the carbonation profiles as well as in the crack patterns that can be seen if pre-existing cracks or openings are present into concrete. In the second results, it can be seen that obviously the carbonation profiles changes accordingly to the new geometry, since the carbon dioxide can diffuse also from the notch, but most importantly it can be seen the difference in the crack patterns derived by a different carbonation profile, since the presence of an opening changes the side from which the carbonation profile approach the steel rebar, and the cracks pattern which forms into the concrete cover is reflect those changes. Lastly, some concluding remarks on the developed model, which is capable to describe the complete process of the carbonation corrosion cracking phenomenon, and it catches also important aspects. For example, the effects of different environmental conditions. It accounts for different material properties changes due to the carbonation process. The rebar swelling is obtained as a function of the corrosion current density, and it is used as a loading parameter to obtain the solution of the displacement and damage field. And the phasefield method allows to obtain crack patterns which actively reflect the different environmental condition we set for the problem. We're still working on this topic, however, we have to fine-tune the parameters to account for a wider variety of environmental scenarios, such as wet and dry cycles, etc. We'd like to add a rust layer as an additional material between the steel and the concrete in order to account for its mechanical effects on the crack pattern. We'd like to add a limiting current parameter for the corrosion process. And lastly, we'd like to extend our model to describe the pitting corrosion due to the chloride ion diffusion inside the concrete. That said, thank you for your attention.